All right, welcome. So today we're going to be talking about calculations using the equilibrium constant. So by the end of this lesson, you guys should be able to follow a procedure, a problem-solving method to determine the amounts of reactants and or products present at equilibrium. Now, the process we're going to learn is a little bit different. This is a new thing, so it's almost like learning dimensional analysis when you're trying to do stoichiometry for the first time. So this is just kind of a new way to solve problems, and it's called a Rice table. And so here's what it starts with. So R is the reaction, which is your balanced chemical equation. And just like in stoichiometry, we're going to need that balanced chemical equation to have those relationships between the reactants and products. I stands for the initial concentrations or pressures. So the concentrations or pressures, if you're dealing with gases, of the reactants and or products that are present before the reaction actually begins. Then we're going to have to figure out how it's going to change. And that's either going to be, adding or subtracting from the reactants or products. So we have to figure out how much is it going to change. And then we have to calculate our new equilibrium concentrations or pressures. So we have to figure out what are the concentrations going to be after the reaction occurs. So Rice tables are a brand new method that you guys are going to use to calculate equilibrium concentrations or pressures of each species. I'm not talking about animal species. A species is what we call a substance, okay? At equilibrium. So we need to figure out how much of each reactant or product remains at equilibrium. Okay, so we have an example here, and I'm already going to go ahead and modify this example a little bit. What I forgot to do was tell you how much dinitrogen tetroxide we're starting with. So this is going to be 3.01 ATM. Insert here, okay? So there we go, typo already. But this is the way it works. So given this equation here where we have dinitrogen tetroxide decomposing into two nitrogen dioxide molecules, and we have a Kp value here of 0.133. So remember that Kp is based on pressure, not on equilibrium, so we should be dealing with pressures in this problem. Calculate the equilibrium pressure of nitrogen dioxide gas if, again, 3.01 atmospheres of dinitrogen tetroxide is placed in a flask and the equilibrium pressure of dinitrogen tetroxide is 2.71 ATM. So lots of information thrown at us at the same time. There's a change going on. We've got to sort out what are starting values and ending values and whatever, and that's what the Rice table is really going to help us do. It's going to help us organize all of that information. So the first thing we have to do is write a balanced equation. In this problem, it was provided to us. It's this equation right here, but it won't always be. So just be ready if you need to write a balanced chemical equation. So we have dinitrogen tetroxide decomposing into two nitrogen dioxide molecules as our products, okay? So there we go. Step one done, have your equation. Okay, so we're gonna use the information that's given to us in the problem to figure out the rest of this table. So I'm going to rewrite it here just so I don't have to keep flipping back and forth. And notice how I kind of space stuff out when I'm doing that first line, the reaction. I've spaced it out a little bit because we are going to be writing values and stuff underneath it. So I want to give, be able to give plenty of room. Okay, so the initial concentrations. So it said that 3.01 atmospheres of dinitrogen tetroxide was placed in the flask. And then it starts talking about equilibrium stuff. So I guess initially all we had was that 3.01 ATM of dinitrogen tetroxide. If they don't mention a starting amount of anything else, then you don't have any. So we put this in the flask. We're going to assume that we didn't put anything else in with it because they didn't tell us we added anything else to the flask initially. So this is our starting amount right here. Now we need to think about how this is going to change. In reversible reactions, it's important not to just assume that everything's going to become products, because it really could go either way. In this case, we can only go forward towards the products. We can only form products because we don't have any products to do the reverse reaction. So I can't make any more N2O4 because I have no NO2s to make it. I do have N2O4s, so I can make some product. So it looks like we're going to be going forward in this reaction. We're going to be moving in this direction. So what does that mean? That means that our reactant is going to be consumed. And so we're going to be losing a certain amount of reactant here. We don't know how much it is, so I'm going to represent that with X. I don't know how much is going to be lost, but I do know that this is going to be consumed in order to make some product. I also know from looking at the stoichiometry of the situation that for every one of these that decomposes, we are going to produce 2 of these. Now before we can fill out the E, let me look back at the equation and see if they gave me any hints. It said here that the equilibrium pressure of the dinitrogen tetroxide, so they gave me an equilibrium pressure here of dinitrogen tetroxide is 2.71 atms. So I went through and I just took all of the information from the problem and filled in what I could, okay? And again, that change line is probably the tricky one, okay? We represent the change, which is that third line, C, using X, okay? We don't know how much it's going to lose or how much it's going to gain, but we do know that it's changing by a certain amount, and algebraically we can represent that using the letter X. We also have to remember that stoichiometry, right? We have to remember that the mole ratio is for every one of these, we make 2 of these. So I have to remember that for every one of these that is consumed in the reaction, 2 nitrogen dioxides are produced. Okay. You can calculate Q using the initial concentrations and pressures. You can compare K to Q and determine which way it's going to shift, okay? And so that's what I was saying. We actually didn't have to do that step here. There was nothing we needed to use to calculate a reaction quotient. Instead, we just knew that product had to be made because there was no product to start the reverse reaction. So this reaction absolutely had to go forward. There was no way that it was going to go in reverse. And so we didn't have to do that step really. But if you are given concentrations all over the board and you're not sure which way it's going to go, you don't know if it's going to go forward or reverse, then you can calculate what's called a reaction quotient, and that will help you determine which way it's going to go. Once you figure out the direction, X is going to be positive for all of the species on the side of the equation. The reaction is shifting toward. So we knew that it was going to shift towards the products. We were going to create products, and so our X value is positive on that side because we're going to be gaining products throughout this reaction. Conversely, X is going to be negative for all of the species on the side of the equation the reaction is shifting away from. So again, reactant is going to be consumed here in order to form products. So we're losing on this side of the equation, we are gaining on the product side. And for like the 12th time already, remember that stoichiometry. Multiply X by any coefficients that are there. And so again, up here, I had a coefficient of 1, and on the product side, we had a coefficient of 2. So for every 1x that's lost here, we are going to gain 2x on the product side. Okay, so then the next part of this is where the equilibrium expression really comes in. We need to write the equilibrium expression. With the given information, with that balanced chemical equation, and then we need to solve for X. So first, let's write that equilibrium expression. Okay, let's do it over here. Since we're dealing with pressures, we are calculating Kp. Okay, remember that Kp is the equilibrium based on pressures. If you see K by itself, then that was based on concentration. If you see K sub C, that was also based on concentration. K has a lot of different forms. Kp is based solely on pressures. They all follow the same rules though. It's always going to be products over reactants with everything held to the power of its coefficient. And so the product in this case was NO2. And the coefficient in front of that product was a 2. So my concentration of nitrogen dioxide is squared over the pressure of nitrogen dioxide is squared over the pressure of N2O4. You might see KP expressions written slightly differently a lot of times. So sometimes you'll see it written like this. The pressure of NO2 is squared over the pressure of dinitrogen tetroxide. So you might see where they actually use the word pressure there to indicate it. But just be aware that both of those would be equilibrium expressions based on pressure. Okay, so let's think about what we've got and what we can fill in to our equilibrium expression. In the problem, they actually gave us a value for Kp. If I look back at it, they gave me a value for Kp. They said that it was 0.133. So I can substitute that value in for Kpp. So I've got 0.133 equals. Now I don't know the concentration of NO2. I don't know what that's going to be at equilibrium. Remember that the equilibrium expression uses equilibrium values, and right now I don't know what that's going to be. But I do know that throughout the reaction we started with none, and we're going to gain 2x, whatever x is. So at the end, I should have 0 plus 2x, which is really just 2x, NO2 in my container. So I don't have a number to put in there, but I can put 2x in there. Now, that's the stoichiometry part of it. The equilibrium part of it is that we also need to square it. So I don't just have 2x on top, I have 2x squared. 2x is the concentration of NO2, but according to the equilibrium expression, that concentration is squared. And so we need to make sure that we're keeping in mind both the equilibrium and the stoichiometry of this reaction. Now we're gonna put that over the equilibrium concentration of N2O4. They actually gave us that. They said it was 2.71. And so we can fill that in right here. And now we have something that we can use to algebraically solve for x. We can figure out the concentration of our product at equilibrium. So mathematically, I would multiply both sides by 2.71 so that this cancels out. And so I end up with 0.36043, I'm not rounding anything at this point, equal to 2x squared. Now, if I distribute that right there, this is going to be 4x squared. So then I can divide both sides by 4. And I end up with 0.0901075, again, I'm not rounding anything, equal to x squared. And then, of course, to solve for x, I can take the square root of both sides. So I'm going to take the square root. And so what I end up with is x equal to, and I can go ahead and start rounding here. So we had about 3 significant figures in all of our answers. And the rule basically is if you don't know how many sig figs, go with 3. And so I got an answer of 0.300 in my calculator. So I now know that x is equal to 0.300. So what I'm going to do is add or subtract x from those initial concentrations to figure out my equilibrium concentrations and pressures. So if I go back, I know that my equilibrium pressure of nitrogen dioxide is equal to 2x. And now I know that 2x is going to be 2 times 0.300, and so that's going to be 0.600. So my concentration of product here is going to be 0.600 ATM. And you know what else we can do? We can actually use this to help us check our work. Because check this out, we started with 3.01 ATM. We were going to lose x and end up with 2.71 ATM. We said x was 0.300. If I take 3.01 and subtract 0.300, I get 2.71. And actually, we could have just used that to algebraically solve for it, but I did want to show you how to use the equilibrium expression. So now I know that my equilibrium concentrations, I'm going to have 2.71, or I'm sorry, my equilibrium pressures. I'm going to have 2.71 atmospheres of dinitrogen tetroxide left, and I'm going to produce 0.600 atmospheres of nitrogen dioxide. So that's how we can use the Rice table in conjunction with the equilibrium expression to solve problems in equilibrium, okay? Let's go ahead and take a look at the next page, because here is another kind of problem that you might see. What if K is actually not given to you? What if you can't just plug and chug into the equilibrium expression? So here's another problem. It says it's at a certain temperature, a 1 liter flask initially contained 0.298 moles of phosphorus trichloride. Okay, now this is important. You've got a 1 liter container and this many moles. Remember that equilibrium is either based on concentration or pressure. It's not based on moles. So always check that. If you're given an amount of moles, then you need to divide by the volume in order to get molarity, right? Because we know that moles over liters is going to give us molarity. We can use this triangle to manipulate that formula. So if you're given moles in liters, you need to divide to get molarity. Now, in this case, we're going to be taking 0.298 and dividing it by 1, so the number of moles actually is the molarity. So we kind of lucked out in this problem. Anyway, we've got this much phosphorus trichloride, and we've got this amount of phosphorus pentachloride. After the system reaches equilibrium, 2 times 10 to the negative third moles of chlorine gas was found in the flask. Gaseous phosphorus pentachloride decomposes according to this reaction right here. So we have an equation. We need to calculate the equilibrium concentrations for everything, and we need to figure out the value for K. So we've got one less piece of information available to us. So first, write the equation. It's a lot of information to sort through, so instead of getting intimidated by it, we're just going to start at the beginning. Write the equation. PCl5, space it out, is producing PCl3 and chlorine gas. Okay? Let's think about what we had initially. It says initially it contained this many moles of phosphorus trichloride. So, and we said that the molarity is going to be the same because it's in a 1 liter container. So the phosphorus trichloride is 0.298 initially. And then we have 8.7 times 10 to the negative third moles of PCl5. Okay, now they didn't mention an initial concentration of chlorine. So again, if they don't say you have any of it in there initially, then you don't. Okay, it then starts to talk about after the system. So that means that none of the other information that's given in this problem is initial information, it's all after the reaction. So now let's think about which way this is going to shift. And one rule that we can keep in mind is that reactions always shift towards 0. Again, the reverse reaction can't occur because we have no chlorine gas to react with the PCl3. So we can't combine these to form reactant because I don't have any chlorine to combine. I do have PCl5 and I could make more product. So if this reaction is going to change, it's going to form more product because that's the only direction in which it could go. So that's why reactions always shift towards 0. Again, let me think about the change. If it's going to shift towards the products, then reactant is going to be consumed. We're going to lose reactant, and we are going to gain product. And since everything has a coefficient of 1, I'm just going to lose 1x here, and I'm going to gain 1x here and 1x here. So every time this decomposes, I get 1 PCl3 and I get 1 chlorine. Now let's think about our equilibrium stuff here. Basically, I need to take my initial values and apply the change. So at equilibrium, whatever is left of the PCl5 is going to be 8.70 times 10 to the negative 3 minus x. On this side, it's going to be 0.298 plus x. And here, it's going to be 0 plus x, or it's just going to be x. So basically, I put these two lines together to form my equilibrium line. Okay, I take my initial concentrations and apply the change. They actually gave us a hint here because what they said was 2.00 times 10 to the negative third moles of chlorine was found in the flask at equilibrium. So again, if they mentioned equilibrium, what they did was they gave us one of these pieces of the puzzle. They gave us this right here, which means that x is equal to 2 times 10 to the negative third. So if x is equal to 2 times 10 to the negative third, then what I can do is substitute that value in for x over here. So if I subtract 2 times 10 to the negative third from 8.7 times 10 to the negative third, then I get 6.7 times 10 to the negative third. So that's going to be my equilibrium concentration of PCl5. And if I add 2 times 10 to the negative third to 0.298, that's actually 0.002 in regular notation. So if I add 0.002 to 0.298, I end up with 0.300. So once I knew that this was my value for x, then I could just subtract it here and I could add it on this side. Remember, the chlorine concentration, or I'm sorry, oh yeah, it is concentration. The chlorine concentration is equal to x, so this is it. We're done there. So those are my equilibrium concentrations, and now it's actually really simple to calculate K, our equilibrium constant, because the equilibrium constant, if we just write the expression, is equal to the concentrations at equilibrium of PCl3 and Cl2, our products, over the concentration of the reactant, PCl5. So there's my equilibrium expression, and I have equilibrium values that I can substitute in here. So I'm just going to drop those numbers in, 0.300, 2 times 10 to the negative third, over 6.7 times 10 to the negative third. Remember your order of operations, make sure you multiply on top to get that product first before you divide. And what you end up with is a value of K equal to 0.0896. There is our equilibrium constant. So I hope you guys can see that even without an equilibrium constant, you should have enough of this puzzle here to figure out what you need to find the equilibrium constant. So remember to use the Rice table in conjunction with your equilibrium expression in order to find your equilibrium constant. When you're doing the Rice table, again, keep in mind not only stoichiometry in this step right here, the change step, keep in mind how we use coefficients to write equilibrium expressions and turn any coefficients up here into exponents in your equilibrium expression. So please be careful with those two things and make sure that you take care whenever you guys are doing these equilibrium problems.